Welcome back to The Explainer. Today, we're bringing a ton of energy to a deeply technical yet absolutely vital topic. If you're a mobile network operator, a CTO, or a telecom architect, listen up, because this one is tailor-made for you. We are taking a deep dive into the evolution of 5G standalone network slicing. Specifically, we're looking at that massive architectural shift from static, rigid configurations over to intelligent, dynamic slicing. We're going to look under the hood at how we're transforming these networks from, basic data pipes into highly responsive, software-driven ecosystems. It's going to be a great one. Okay, let's quickly outline our roadmap for today. We'll start with 5G SA network slicing, contrast static versus dynamic slicing, and cover the role of URSP. Then we'll walk through the URSP dynamic steering workflow, how we provision those rules, and finally, network agility and monetization. All right, Section 1, 5G SA network slicing. Let's get right into it. Now, as telecom architects, we all know the ultimate objective of this architecture, right? It's about guaranteeing a strict quality of service that's tailored to very specific usage models. We're really dealing with three core pillars here. First, there's eMBB. That gives us the massive throughput required for heavy data lifting, like streaming 4K and 8K video. Then we have URLLC. This gives us that ultra-low latency, which is literally non-negotiable for critical industry applications, and connected vehicles. And finally, mMTC, which is built to handle the massive density of IoT connections. Think thousands of urban sensors deployed across a smart city. Network slicing is exactly what allows us to deliver on all three of these simultaneously without a single one compromising the performance of the others. But achieving this kind of strict isolation and performance guarantee, it relies entirely on the 5G standalone core, or the 5GC. Legacy architectures simply can't do this dynamically. By utilizing a service-based architecture, or SBA, our network functions communicate seamlessly via APIs. And this API-driven framework is essentially the engine room. It's what makes end-to-end network slicing technically feasible in a 5G SA environment. Moving right along to Section 2, static versus dynamic slicing. So, when we look back at basic early-stage slicing, it relies on a static identifier, the SNSSAI, or Single Network Slice Selection Assistance Information. In this legacy approach, the slice assignment is decided right at the initial registration phase by the AMF and the NSSF. But here's the bottleneck. It's incredibly rigid. The user terminal is just tied to that slice regardless of what application is actually launched. If a user suddenly starts a high-priority app, too bad, they're stuck on that default slice. Dynamic slicing completely shatters this limitation. By introducing URSP at the application level, we empower the terminal itself to intelligently switch between network slices in real time. It matches the exact needs of whatever app the user just opened, right in that moment. Which brings us perfectly to Section 3, the role of URSP. So what exactly is making this dynamic switch happen? It's URSP, which stands for UE Route Selection Policy. Think of URSP as the critical software bridge between the device and the network core. Basically, it's a specific set of software rules that are pushed directly to the user equipment. These rules dictate exactly how to route each specific data flow to the correct network slice. By giving the terminal the intelligence it needs to categorize and route its own traffic flows dynamically, URSP completely removes the guesswork and those static bottlenecks we used to deal with. And here is where it gets incredibly practical. This isn't just some theoretical architecture on a whiteboard. This is being integrated right now into modern operating systems, like Android 14 and above. The OS actively detects the specific needs of an application. So, for example, if a user boots up a cloud gaming app, the operating system knows, hey, I need incredibly low latency for this. It instantly applies the corresponding URSP rule to push that traffic onto a URLLC slice. And honestly, the best part is that this entire routing optimization happens completely transparently to the user, ensuring an automated, flawless experience every single time. Let's look at how this actually plays out in Section 4. URSP Dynamic Steering Workflow. Let's walk through this step-by-step technical signaling flow. We'll use a critical telemedicine application as our scenario here. So, Step 1. The user launches the telemedicine app, which inherently requires high reliability and low latency. Step 2. The terminal instantly queries its internal URSP rules database to find a match for this specific high-priority, low-latency requirement. Moving to Step 3. Based on that rule match, the user equipment selects the specific authorized URLLC SNSSA. And finally, step 4, and this is the absolute key architectural trigger here, the SMF, or Session Management Function, receives the selection and actively configures the UPF, the User Plane Function. This establishes a dedicated, optimized data session, so you get an end-to-end guarantee created right there on the fly. Next up, Section 5, Provisioning URSP Rules. Now, as architects, knowing how it works is great, but we also have to know how to deploy it. We generally have two primary methods for provisioning these URSP rules out to the terminals. Method 1 relies on device management. In this scenario, a mobile device management platform, an MDM, or an entitlement server literally pushes the rules down to the terminal before it even connects to the network. This is a highly effective route for corporate fleets or managed enterprise devices. Then we have Method 2, which is much more dynamic and network-driven, UE Policy Association. During the connection phase, the network's policy control function, the PCF, establishes a policy association and pushes the URSP rules over the air. And this is based dynamically on the specific subscriber's profile, which obviously offers incredible flexibility for consumer and broad enterprise markets. Finally, let's wrap up with Section 6, Network Agility and Monetization. From an architectural standpoint, we are fundamentally moving away from just managing dumb pipes. By embedding this intelligence right at the edge, URSP transforms the user terminal into an active, intelligent actor within the overall network ecosystem. The device isn't just passively receiving data anymore, it's actively collaborating with the 5G core to optimize its own traffic. It's a real game changer. And this shift leads us directly to a massive monetization breakthrough for mobile network operators. We're talking about true slicing as a service. Because we can guarantee specific performance parameters on a per-application basis, operators can finally transition away from just selling generic gigabytes of data volume. Instead, you can now monetize guaranteed dynamic service levels. This creates entirely new high-value revenue streams in both the B2B and premium B2C markets. I want to emphasize that URSP and dynamic slicing aren't just neat optional features. They are the non-negotiable architectural foundations for the next generation of critical services. As we look ahead, think about use cases like distributed artificial intelligence, autonomous drone fleets navigating complex city infrastructure, or connected health services like remote surgery. Literally none of these can function safely or effectively on a static, best-effort network. They absolutely demand the dynamic agility and strict quality of service that only URSP-driven slicing can provide. So, I want to leave you with a final provocative question to take back to your engineering and strategy teams. Look closely at your current roadmap. Is your 5G core truly ready to dynamically support the strict, slice-specific demands of tomorrow's critical services? Or are you still architecturally bound to the rigid, static pipes of the past? The transition to software-driven, intelligent edge routing isn't just coming, it's already here, and it is time to build for it. Thanks so much for diving deep into this explainer with me, and I'll catch you in the next one.